I'm Julia Caserto, a member of the Minglan Ma Lab in Biological and Environmental Engineering. Today I'm going to talk about a strategy to detoxify neonicotinoid insecticides. Neonicotinoids are a class of insecticide, and they've been shown to have impacts on bee health and learning behaviors, so this provides motivation to develop technologies to help protect them from their sublethal and lethal effects. In this work, we develop microparticles to capture imidacloprid, which is an example of a neonicotinoid insecticide. Our preliminary data suggest a nonspecific binding phenomena in aqueous environments when we compare molecularly imprinted particles with control particles that aren't imprinted. Future work will aim to develop greener particles, so using a method that doesn't involve as many organic solvents or toxic reagents. And we also want to promote efficacy in aqueous environments, so we will consider methods other than molecular imprinting. Neonicotinoids are an insecticide that target nicotinic acetylcholine receptors. They lead to paralysis and death of insects, and they preferentially bind to insect receptors. They're used often in agriculture to protect crops from undesired pests, but their effect on bees is a big concern. They're also water-soluble, so they can contaminate soil, groundwater, and plants, which will in turn affect pollen and nectar, which is consumed and transported by bees. Imidacloprid is one of the widely used neonicotinoids, so it was chosen as the pesticide of interest for this study. Molecular imprinting aims to develop three-dimensional cavities or binding sites that promote selective adsorption. There are some challenges when considering this technology, such as controlling cross-linking and swelling behaviors, because swelling can affect the morphology of the binding sites, thus impacting the adsorption properties. There's a couple approaches: non-covalent, covalent, and ligand exchange. Overall, there's a functional monomer, which will bind to your target, a cross-linker to help form the three-dimensional cavities, and your porogen and the target of interest. So you'll perform your reaction to get your particles or polymers that are imprinted. Then you need to wash or remove the template, which is your target molecule, out of the cavity. So then you hope that when you put it back in an environment with the target, that it will capture it. I used a fairly straightforward precipitation polymerization technique to make these particles using methacrylic acid as our functional monomer. You can see the particles are fairly small, around 2 micron. We want particles that are smaller for this situation because we need to make sure they're able to be consumed by bees and enter their digestive tract. Another key step is actually removing imidacloprid from the molecularly imprinted particles after synthesis, because we need to make sure they're removed so then when we want to actually apply to our experiments, it can still bind on to the sites. It took about 7 washes in order for the imidacloprid to no longer be detectable by each PLC, as you can see from the graph above. Next, we have an in vitro experiment to test the binding capabilities in an aqueous environment. It was found that there wasn't a statistically significant difference between the molecularly imprinted MIP and the non-imprinted NIP groups. We think that this is due to hindrances in hydrogen bonding because the interaction between methacrylic acid and imidacloprid relied on hydrogen bonding interactions. So in order to test this, we could repeat in an organic solvent such as acetonitrile. Main conclusions: molecular imprinting may not be the best option for this application due to the loss of adsorption capacity in aqueous environments and the high number of washes that are required to remove the template after synthesizing. So this could become costly when we consider future scale-up and commercialization. Also, for future work, we want to decide particles that are greener and don't require as many toxic reagents and solvents during processing. We also will consider other polymerization and detoxification methods other than molecular imprinting. In vivo experiments will also be utilized to assess if our technologies, this one and others that are developed, are able to not only promote survival, but prevent sublethal effects, such as effects on flight or ability to move through water. So, here are my references and funding source. Thank you for listening.